Okay, so as always, let's start with a quick recap. And before I even do that, let's introduce a notation that will somewhat help us to go through all of these together as a unified thing. So we have already been talking about Lie algebras and their subalgebras, because Lie algebras are vector spaces on which you have a product called the Lie bracket defined. And we have already talked a lot about the properties of the Lie bracket, namely that the Lie bracket has to be anti-commuting. It also has to obey the Jacobi identity. That is, it has to be non-associative in a particular manner. In addition to that, we have introduced the structure constant for Lie algebras, basically by looking at the bracket of two basis vectors, expanding that in basis vectors, and calling the coefficients that come in the CKIJs, the structure constants for the Lie algebra. And of course, as the way we came upon this was, we started talking about Lie groups, and then we talked about what happens close to the identity with the Lie group. And finally, we found that for any set of functions to be given, any bunch of eta jk's to be given, which can give us the composition function of the Lie group back, you need a bunch of integrability conditions. And from there, we had structure constants for the Lie group. But then we also saw that if you look at the tangent vectors to the one parameter subgroups of a Lie group at the origin, these tangent vectors inherit from this basic structure of the Lie group a kind of bracket operation, a kind of product between two such tangent vectors, and that essentially gave us a motivation for going into Lie brackets in the abstract. We also saw that the definition of a Lie subalgebra, that is a subvector space of the given Lie algebra. Remember, Lie algebras are vector spaces. So a subalgebra has to be a subspace which is closed under the bracket operation. Now, the notation I've been talking about is the following. If A and B are two subalgebras of a Lie algebra L, then we would define this bracket between A and B. Of course, our original bracket is defined between elements of the Lie algebra. Here we are talking of two whole subalgebras, which are collections of elements, and we are trying to define a bracket between these two. So this is defined to be the span of, or in other words, the set of all possible linear combinations of. Span is just a standard term from linear algebra, which I'm pretty sure all of you are familiar with. All Lie brackets, all Lie products, whatever you call it, of the form x comma y, where x belongs to capital A and y belongs to capital B. So two questions which I will leave you to worry about. Question one, is this, just hold on. Okay. Now, if,
Sir,
yeah,
uh, what do you mean by span?
okay, that's what I stated, although, okay, span is if you have a bunch of vectors and you take all possible linear combinations of them, that is called a span. Okay, all those vectors.
All
Assume
possible
that is linear
combinations.
algebra, right? This is a linear algebra statement.
Okay. Yeah.
Hmm? And so the question that I have is in essential in this connection, which is number one is a sub is A comma B a Lie subalgebra of L? That's the question. That's the first question that I want you to think about. And question two, how are A comma B and B comma A related? Think about these things. I'm not going to tell you what these are, but it's pretty straightforward. You should be able to figure out yourself. But some amount of thought may be needed for both of them. Okay. So we defined a subalgebra, of course, before. In fact, you need to define a subalgebra even before you begin to talk about these things. But strictly speaking, you could also talk about this if A and B were just two subsets of L. Didn't have to be subalgebras. If A is a subset of L with some elements, B is another bunch of elements, you could just take brackets between those elements and then form the span. And then you might again ask the question, if A and B are not subalgebras but are actually just subsets, what is the status of this bracket between A and B? Is this a subalgebra or is it not? So I will leave you to worry about these things. It's pretty straightforward algebraic. It's a very straightforward algebraic issue. You should be able to figure it out yourself. Okay. So now we come to just defining subalgebra in terms of these brackets that we have just introduced. Although frankly, that would really be an impossible thing to do. We started saying that A and B are subalgebras, right? But this is not really a definition. It's more of a convenient way of writing the definition. So A is a subalgebra of L. In fact, this is the reason why we have to, if you want to even state this, you have to define the bracket between arbitrary subsets. Because you cannot even, if when you say A is a subalgebra of L, if certain thing happens, then you should be able to do this, whatever okay, if what? If this happens. If the bracket of A with A is what? Can anyone tell me what that will be? If A is a subalgebra of L, then what A bracket A comma A tells you? A comma A is by the, it has to be simply A, because you're just taking commutators of elements from A that has to be in A, and you're taking the linear combinations. Remember, A is being a subalgebra is also subspace. Any set of linear combinations, of course, will be in there. But in order that this definition at all makes sense, you of course have to be able to define this between arbitrary sets. So, warning, this looks like the same thing as a Lie bracket, but it of course is not. It's a derived concept from a Lie bracket. After all, if this had been a Lie bracket, if you took the Lie bracket of an element with itself, it would definitely have to give you 0, right? Because of the anti-commutativity. But this is, of course, not that thing. Okay. So we had this notion of a subalgebra, which we have rewritten now in terms of this bracket. We also had a notion of an invariant or normal subalgebra, also very often called an ideal of the Lie algebra L. So ideal, invariant subalgebra, normal subalgebra all mean the same thing. Well, we say that if you took the Lie bracket between between an element of A and any element of L, the result would be in A. In general, of course, that's not true. For a subalgebra, okay, first of all, if it is this is the first part, it has to be a subalgebra. It is a subalgebra, number one. That is, of course, A's bracket with A has to be A. For subalgebra, that's all you require. If you take two elements from A and take the Lie bracket, you are going to get an element in A. But now you are insisting that if you take a Lie bracket between an element of A and any element of L, the result will be in A. And therefore, this is the condition for an ideal. That is, this of course expresses the fact that if you take something from A, something from L, form the commutator bracket, and then of course take all possible linear combinations, you're going to stay within A, and that's it. Is that okay?
Yes, sir.
Okay. Now we also stated these results, and I'm just going to quickly remind you of these. If A is an ideal of L, then L quotiented with A. Remember, L quotiented with A means you are going to identify any two elements of L which differ by an element of A as equivalent to each other. We are going to form equivalence classes and talk about the set of those equivalence classes. We showed that this is a subalgebra, also called, or this is actually isomorphic to a subalgebra, to be more precise. It's a Lie algebra in itself. And here, obviously, the rule is you define the vector addition by this, multiplication by scalar by this. And the other important operation that you have to define, which is what is the Lie bracket between the class X and the class Y? And that is obviously the only possible definition which could make sense. You form the Lie bracket of X and Y and take its equivalence class. We showed the other day that basically because A is an ideal, or this definition will be well defined. Okay? If A were not an ideal, this would not be a proper definition in the sense that if you took, instead of X, X prime, another element of the class of X as a label, and instead of Y took Y prime, and form the Lie bracket of X with Y, X prime with Y prime, and found this equivalence class, you might very well have ended with a different result. So if A were not an ideal, this Lie bracket definition would not have been a proper definition, which is why the ideal plays an important role here. Okay, so that was almost all except that, yeah, we also talked about. Did we talk about solvability in the last class? I don't remember. Yes?
I don't think so, sir. I'm not sure.
Okay, anyway, I do remember I talked about the commutator algebra, right?
Yes, sir.
Any Lie algebra, even a Lie algebra L, its commutator also known as derivative. Okay, that's, I stopped too soon. The left too little space there. Derivative subalgebra is L1, which is defined to be the bracket between L and L, which means take all possible commutator brackets of L and then take their possible linear combinations. Okay. Note that taking the span of the commutators, or I should really say commutator, that's bad habit. Being a physicist, that habit always persists. Because for physicists, most of the time, the Lie bracket operation is a commutator. What I really should say is take any two elements of L, form their Lie bracket, and take their all possible linear combinations. That's the span part. Now, when we were talking of two arbitrary subsets of A and B, then why we did not stop just at saying take all possible commutators, but ended up saying take all possible commutators and then take all possible linear combinations? You should think about why we had to do that. And you should also think about whether, in this case, when you're talking about the commutator subalgebra or the derivative subalgebra, it is at all necessary to say, let's take the span after for taking all possible commutator brackets. In other words, do you understand what I'm asking here? Let's see. Yes?
Yes, sir.
So when I am saying that is it at all necessary to the span, I'm really asking you that if you had not taken the span, remember when you take, say you're taking two elements from L is a vector space. So you could start out by taking any kind of linear combinations you want. So the question is it at all necessary to take the span after forming the commutators, or just say take all possible commutators would have been enough in this case? Note that in this case, we are taking the bracket of L with L. So all possible linear combinations are already in. So this is something I want you to ponder about. Would it be necessary to take a span here, or would it be okay even without taking the span? Would we get the same thing? I'm not telling you that it will not be the same thing, or neither am I telling you it will be. Think about it again. This is something which will give you enough exercise in thinking about these things as to whether. So here the question is the span or take all possible linear combinations at all necessary here? Of course, before you even try to answer this, you should first address why was it necessary in the original definition. And if we are originally defining A comma B as the span, then of course L comma L will automatically continue with the definition. But I'm simply asking this, that if we were only interested in the commutator subalgebra, would we have been within our rights to just drop the span from the definition? Note once again, I'm not giving you either a yes or a no as an answer. I will ask you to think about it. Last day, we gave some examples of this. For example, if L is SO3, we saw that L1, of course, sorry, this is wrong. L cannot be capital SO3. Capital SO3 is a notation for the group. This is small SO3, the corresponding G algebra, which is our familiar angular momentum algebra apart from the factor of I. Okay? Then L1 would be just all possible commutators of SO3 elements. And then you might even take a span after that. But it's easy to see that because Lx and Ly's bracket gives you Lz, Lz, Lx, Ly's bracket gives you Lx, and so on. This L1 has to be the same as SO3. Okay? Take
Yes,
Yes,
sir.
sir.
But the other extreme of this, so there are examples where the derivative subalgebra or the commutator subalgebra is the subalgebra itself, is the algebra itself. Okay. The other extreme example of this is if L is abelian, then L1 is how much? If it's abelian, which means, what does it tell you about the brackets?
All element brackets are 0.
All brackets between elements are 0. And then if you form the span of a bunch of zeros, that is, you linearly combine a lot of zeros, you are only going to get 0. So L1 is going to be the vector space and a Lie algebra whose only element is 0. We don't usually put a curly bracket around 0 here, we just say 0. Okay. Remember, a vector, this is not empty, by the way. Don't confuse this with the empty set. An empty set has no elements. Any vector space has to have at least one element, the null vector. This 0 here is just the null vector of that vector space. And that's the only element. So if L is abelian, then in one shot, L1 becomes just 0. That is no other
Sure.
element. Yeah. Yes?
So does that mean that if the group has a non-trivial center, say the group has a trivial center, then the commutative subalgebra is equal to 0?
It is a trivial center.
Not in this case, or abelian case, it's the entire group. The center
Yeah.
is the entire group because everything commutes. But in SO3, it's a trivial center,
Right.
and so that's why the commutative subalgebra is the same as the group.
Not necessarily. That is, without that happening, this would never have been possible. Okay. So since L, so think about this. This is again something you should be able to think and figure out. There are two questions here. Okay, you are asking a question, but I think you are here confusing the converse of what you wanted to say, or what would have been correct to say, with what you are really saying. Just think
Yes, I
about
was saying that if it has like a trivial center, then is the commutative subalgebra the same as the original algebra?
it. Well, you were saying that. What I would say is, does it have to be? Think of it. Suppose a system did not have a trivial algebra, trivial center, a non-trivial center. Does it necessarily mean that its commutative subalgebra cannot be itself?
No, it might be the case that the
So
elements in
think
the
about
span.
it. The two may not be related to each other. After all, having a non-trivial center essentially means there are elements which commute with everything, right? But then it's not an abelian group, so there are other elements which do not commute with everything. And when you take the span of the commutators of those elements, it is possible that you are going to get the whole thing back. I'm not saying you must, but I'm saying it might happen.
Okay, sir.
Okay, now two important properties of the commutative subalgebra. One is L1. This L sub 1 is always a special notation for the commutative subalgebra. Sometimes we also use L prime. After all, prime is a notation for derivatives. So L prime is something sometimes often used. However, it might be that you would very often use L and L prime as two subalgebras, or one as a subalgebra of some kind of subalgebra of the other. So I will not use L prime. I will just say L1. This is lower one. Okay. Now this is the notation, but this is an important question. Important point. L1 is always an ideal of L. Okay. Now, how do you show that? Remember, L1 is span of all Lie brackets of any element of L with any element of L. Now, so those results are, of course, elements of L, right? No problem with that. First of all, it has to be a subalgebra. Oh, sorry, it has to be a subspace. Yeah, it has to be a subalgebra. That is, a subalgebra should be sort of trivially obvious. If, first of all, is it a subspace? The answer is here you don't even have to think of that, because the moment you say span, take all possible linear combinations off, then you have at least ensured that whatever you have got is a vector subspace. Is it closed under brackets? It will better be. After all, if you take any element, you are going to get is an element of L, right? Any element you get in L1 are linear combinations of brackets of elements in L. But brackets of elements in L are, of course, elements of L. A bracket is an element of L. And if you take many such brackets, they are all elements of L. You are linearly combining them. L is a vector space, so that is of course an element in L, right? So if you take brackets of two elements from L1, it had better be in L1, right? Because brackets of any two elements of L has to be in L1. Is that okay?
Yes, sir.
Okay. But what is maybe not so obvious, but it's still quite obvious, that L1 is not just a sub-algebra, it's actually an ideal. Why? Because if you took an element from L1, which of course is an element of L, and took any element of L, not necessarily in L1, to form the bracket, what will the result be? It will be a bracket of two elements of L, so it has to be in L1, right? In order to be an ideal, what you need is to ensure that if you take an element from the subalgebra and take any element from the original algebra, the bracket is in the subalgebra. That's trivially true for L1, right? By virtue of it being the span of all possible brackets. Is that okay?
Yes, sir.
Okay, the next important sub point which comes here. Of course, if L1 is an ideal, then L by L1 is a subalgebra. You've already seen that before.
Right.
But now notice that any element of L by L1, what will that be? Any element of L by L1 will be equivalence classes, of course. And what about the bracket of two elements of L by L1? You take any two elements of L by L1, you have a equivalence class of X, which means X minus, so collection of all vectors in L whose difference from X, all vectors Y such that Y minus X is in L1, right? That's what the bracket X is. I should not have used Y because I'm going to use Y as some other element. And here you have any bracket of Y. So these are all elements which differ from X by an element of L1. These are all elements which differ from Y by an element of L1. And we form the D bracket. Now, by the virtue of the definition of a factorial algebra, this has to be this. Right? The equivalence class of a bracket. Right? But what can you say about the bracket? Yes? What can you say about the bracket? In other words, can you identify a set which this bracket is definitely an element of? Again, this is trivial. Remember, L here we are not saying anything about any special L. This is for all L, right? Given an L, if we take two elements X and Y, remember these are equivalence classes. But here what I am doing is forming the bracket of X and Y first, and then taking its equivalence class. We have already established that because L1 is an ideal, this is going to be a proper, well-defined bracket operation. But this bracket is the original bracket of the Lie algebra, right? And which set does this belong to, this bracket? Which set that we are mentioning here? Hmm? Yes? This quantity, a bracket, belongs to one of the sets that we are talking about.
It definitely belongs to L.
Of course, it definitely belongs to L, but that would be rather trivial to say. It also definitely
It belongs to L1.
Right?
Yes.
Which means that it differs from 0, the null vector. By what? An element of L1? Namely itself, right? This is a member of L1, which means it's actually in the equivalence class of 0, right? Yeah.
Yes.
And this obviously is the null vector. The equivalence, remember our definition of addition between equivalence classes was this. So in this quotient space, which L by L1 is, which in general L by any ideal would be, which is null vector. Null vector is the equivalent. Null vector here, remember, when you say vector, it's not one single vector of L, but an equivalence class. Which equivalence class? That of 0, right? Because if you were to add to the equivalence class of X, the equivalence class of 0, you would get the equivalence class of X plus 0, which is of course the equivalence class of X back. So the equivalence class of 0, which obviously is nothing but the set, the algebra, the subalgebra, the ideal A itself. Remember, every element of A differs from 0 by an element of A, which means obviously A is the equivalence class of 0. So this I could call L1 in our specific example, or it's just the null vector of L by L1, right? So what does this tell you about L by L1? What kind of Lie algebra is it? You're taking any two elements of it.
Abelian.
So this has to be abelian because the Lie bracket between any two elements of L by L1 is 0, the null vector of that set, right? So two important properties. If you form the derivative subalgebra, it is a subalgebra. Not only that, it is an ideal, and because it's an ideal, you can form the factor or quotient subalgebra, and that has to be an abelian subalgebra of L. Is that okay? Or at least it has to be an abelian algebra at this stage, right? Now, yeah, any questions? Okay, if not, now one thing. If L1 remember is a finite dimensional vector space. After all, if you think of L not as an abstract Lie algebra, but one that was derived or was obtained from a Lie group, then it has to be a small r dimensional Lie algebra, or the underlying vector space has to be a small r dimensional vector space. So if L1 is not the same as L, what can you say about the dimensionality of it? Remember, L1 is a vector subspace, right? Of course, a vector space is also trivially a subspace of itself. So it could very well be the same space itself. L1 could definitely be L. We have already seen an example of that, namely SO3. Right? L1 is the same as L. But if L1 is not the same as L, what can you say about the dimensionality of the vector space L1? Either L1 is equal to L, or dimensionality of L1 is what? Come on. Pretty easy. For every finite dimensional vector space, what is the relationship between the dimensionality of the subspace and the dimensionality of the space? That's a trivial statement.
Should be less than.
Less than equal.
Well, it should be less than equal to in general, but if it's equal to, then L1 will be the same as L. So dim L1 should be less than dim L. Or L1 should be equal to L. Right? Clear? So now what we do is we essentially keep on repeating this. That is, L is the original Lie algebra. From that you get a invariant subalgebra by just taking this. It is derivative subalgebra of L. But why stop there? You can take the derivative subalgebra of L1, call that L2. Take the derivative subalgebra of L2, call that L3, and continue. In general, define Lj plus 1 to be Lj with Lj, right? At each stage, this is for the original algebra, this is an invariant subalgebra of L. What is L2? It's an invariant subalgebra of L1. What is L3? It's an invariant subalgebra of L2. In general, Lj plus 1 is an invariant subalgebra of Lj, right? Now, if you think of this sequence, of course, at each stage you have an invariant subalgebra, and the factor algebra in each case has to be abelian. Factor algebra meaning L1 factored off by L2, L2 by L3, Lj by Lj plus 1, and so on. Now, if you keep on doing this, what will happen to the dimension?
It will go on reducing,
Not really, but you are close.
or will remain the same.
Or will remain the same. But if it, so may not happen at the beginning. Maybe in the beginning it may reduce, but then after 2 steps, it keeps staying the same. So of course, if it keeps staying the same, if L2's dimension is the same as L3's dimension, then L3 essentially is the same as L2, right? Has to be. Right? Unless L1 is equal to L, dimensionality is less. So the same goes for every stage. So either the dimensionality goes on reducing, or at some stage, maybe after 3 steps, maybe after 4, maybe at the very beginning, what you get is something like this. L becomes L1, then L2, but then L3 is, let's say, equal to L2. Could be L3, could be L5, can't really specify then. But then if L3 is L2, what is L4? L4 has to be the same, right? L4, if L3 is L2, that means L2, L2 is L3. So L4, which is L3, L3 is nothing but L2, L2. So it has to be L3 itself. And so on. Right? So this derivative series, the sequence that you are going to get, stabilizes at some value. That's possible. What is the only other possibility? Can it keep on reducing forever?
It goes to 0.
Yeah, because the point is you're starting at R, and at each stage it has to either stay the same, which means you have got into this kind of a stable situation, or it has to ultimately end up being 0, which means there could be, or there could exist some J or some N for which ln equals 0. 0 meaning here, again, the 0 vector space, the vector space is only 0 as the element.
Sir,
Yeah.
if it is like stabilizing, then how can it go to 0?
If it is stable, then it won't. I'm saying, what is the other possibility?
Oh, other person. Okay.
Or,
Oh, okay.
okay, I should have said else, perhaps. Either this happens. If it doesn't happen, if it doesn't reach a stable state, so at some stage, Lj plus 1 is equal to Lj doesn't happen. Of course, it always happens. The point is, it either happens before you hit the null vector, the trivial vector space, or it happens after you hit the trivial vector space, which is the case here, right? Once you hit the trivial vector space, in fact, this n, this number, what can you say about it? What the number for which ln becomes 0 for the first time. Of course, if ln becomes 0, then ln plus 1, ln plus 2, ln plus 3 are all 0. Let's say ln is
It's a
0,
dimension of L.
so n has to be, so dimension of L was R, right?
Yeah.
N has to be what?
Less than
Less than or equal to R.
Hmm.
It cannot exceed R, right? Because every time you're dimension has to be reduced by at least 1, which means you're starting at R, you get at most R steps, right? Is that okay? Can be less than R, by the way. In fact, you have already seen an example of where it's less than R. It's 1 for every abelian group, right? No matter what dimension your abelian group has, your abelian group may be 20-dimensional, but L1 will be 0, which means in that case, this sequence stops at L1. But in general, what we are talking about, so here, this is the sort of generalization of the notion of abelianity. Abelians would have stopped immediately, but a group may never stop like this, or may stop after a number of steps. And if this happens, it means it stabilizes only at 0, not before. Then the Lie algebra L is called solvable. This is a very important notion in abstract Lie algebra theory. Even I distinctly remember talking about this last time, because I said that although this is a very important notion in abstract Lie algebra theory, it's not so important for us as cases, because most of our physics examples are cases which are not solvable. Because they are not only not solvable, they're a special kind of thing which cannot be solvable as part of the definition. Okay. However, solvable Lie algebras do form a very important part of the mathematics of Lie algebras. And not only that, this is also an important issue. We will see that there is a theorem which says all Lie algebras can be thought of as being made up out of a solvable piece and another piece. The second kind of piece is essentially what we are going to talk about. Solvable piece and what is called a semi-simple piece. It is semi-simple Lie algebras which we really should focus upon, because at least as physicists, those are the ones which are most commonly used for us. Doesn't mean that solvable Lie algebras are never used. It just means that they are not that useful, or not that common in physics. Okay. But since we are on this topic of general classifications, since we have already talked about solvability, although we are not really going to use that much in the rest of the course, let me also bring, since we are in for a penny, let's go in for a pound, and let's talk about the other kind of classification or other adjective that we can put to a Lie algebra, which again is not really very useful for us, but follows a similar kind of notion. Basically, we had this sequence, right? L0, which is L. Then we went to L1 by forming a derivative. Then we took L2, L3, which means derivative, of course, means bracket with itself, and so on. And if this sequence terminated at 0, we said it's solvable. If it never terminated, it kept on repeating forever at a non-zero value, then it's not solvable. But apart from this one, we could do something else. We could define L1, okay, as this. Same as we define L1 this way. Remember, the difference is that here we are using a superscript. But of course, this means L1, upper one is the same as L0. The difference lies in the next entries. L2, L upper 2, is defined not as a bracket of L1 with itself, which is not as a derivative algebra of L1, but a bracket of L with L1. So you're taking all possible commutators between all possible original L elements and L1 elements, and taking the span. That gives you L2. Then you get L3, which is L, L2, and so on. So here, the superfixed ones are defined this way. Can you see the difference between the two cases? Here, what you were doing is taking each stage and taking their bracket, that is bracket themselves. Here at each stage, you're taking the bracket with the original L and forming this sequence of subalgebras. Okay? Right? Okay, and now, okay, now tell me one thing. Can you, of course, L1 is the same as L. What can you say about L2 and L lower 2? Sorry, L1 is not the same as L. L1 is the same as L1. One is the suffix, the other is the suffix. How are these two related? Let me remind you once again, L upper 2 is already written here. L lower 2 is L1, L1, which is the same as, of course, L upper 1, L upper 1. In L2, you take commutative brackets of elements of L1, L lower 2. You take commutative brackets of L1 with itself. And in L upper 2, you take commutative brackets of all elements of L with L1. Can you say what the relation between the two?
The lower two will be a subalgebra of the upper two.
Yeah, at least it should be contained in, right? Okay, I got the sign wrong. I never could remember which way it goes. Right? L upper 2 should contain L lower 2. Not only that, it should be pretty easy to see that this should happen. Contain doesn't mean it has to be strictly bigger than, could also be equal to. Right? Is that okay? So now, other than the sequence that we had with L0, L being L, then L1, L2, L3, L4 with all suffixes, which you actually get by forming commutative bracket after commutative bracket after commutative bracket, or derivatives of in sequence. But also get this sequence. L0, which is of course the same as L. L1, which is the same as the upper L lower one, but then L2, L3, and so on. Right? So if you get this, it's also possible. And now, similar nomenclature comes in. If ln is 0 for some n, that is, if this sequence terminates at 0, this is a different condition from L lower n being 0, because of course these L's are being created in different ways. Then the Lie algebra, this is of course a statement about the original Lie algebra. L is called, this is the name of course, it's called nilpotent. Again, not really very useful for physics, but very useful for general Lie algebra theory, and sometimes rarely useful for physics as well. But since we have gone this far, can you tell me what is the connection between nilpotency and solvability? That is there a link? Does one imply the other, or the other way around?
Nilpotent guarantees solvability, I think.
Right, because nilpotent would of course mean that n, there is some n for which L upper n is 0. And since L lower n is contained in L upper n, of course, if the set containing one has only the null vector, then the set contained must have only the null vector. So nilpotent implies solvable. Of course, it doesn't say that if, say, L upper 5 is 0, it doesn't mean that L lower 5 is the first time it becomes 0. It could have been L3 has already become 0. L lower 3. But if it's nilpotent, then the algebra has to be solvable. Not necessarily the other way around. Okay? Now, next comes the most important part of the definition. By the way, I was told that you're looking for textbooks, right? You have found the one? The textbooks for this part?
Yes, sir.
Okay. Now, let me also warn you that there are certain places where that book makes some mistakes, or not really mistakes, but is not perfectly accurate. So please don't rely only on that book. Just also use your, well, use your sense of logic. Having said that, now let's come to the more important classification of
Uh,
yeah. Yes.
Sir, what for the ones that are not that are solvable and are not nilpotent? Like
Good,
what
very
properties
well.
would
So that's all good. That's all good. That's, you,
okay.
you could have nilpotent Lie algebras, but you would know by virtue of them being nilpotent, they already have to be solvable. But there could be other solvable algebras which are not nilpotent. So solvability is actually a larger class, right?
Okay. Yes, sir.
The more solvable the algebras are the nilpotent Lie algebras.
Okay.
Oops. Sorry, I've just lost my earphone. Yeah, I managed to connect it. So if somebody says something in between this nilpotent solvable business, I better repeat it. I don't think I lost my earphone for a long enough interval for that to happen. Okay, now the most important classification for us faces. A Lie algebra is called, I should actually use a different color to highlight this. Simple. If, and this is very important, simple and semi-simple. These are the two important classifications of a Lie algebra. It has no proper no proper ideal. Proper ideal simply means, remember, every Lie algebra, okay, let's start with them being vector spaces. Every vector space has two trivial subspaces. Proper is the same as non-trivial. Which are the two trivial subspaces every vector space has?
Null and the vector space itself.
Null meaning, of course, the vector space which has only the null vector. And like that.
Yes.
And also, it's obvious that both of these are ideal. The full space has to be ideal by definition.
Yes.
What does the null vector space? So you form a bracket with zero, you are always going to get zero. That's guaranteed. That's guaranteed. By the way, how is that guaranteed? That bracket with zero has to be zero. Which property of the bracket actually ensures that you that 0, x is 0? What are the properties of Lie bracket that you know about? Anti-commutative,
From the scalar property of this bracket.
from the fact that
Scalar multiplication.
Mhm. From the
Scalar multiplication of this bracket.
yeah, basically not from the Lie bracket property, but from the fact that it's a product. Every
Yes.
product has to play nicely with linear combination. And because the null vector 0 can always be written down as zero, the number 0 times any vector. And a Lie bracket is always uh, linear. The result will be the number 0 times whatever vector you have chosen, bracket with x, which means the number 0 times some vector, which will be the null vector. So this has to be true for all algebras, by the way, not just Lie algebras. Because this does not rely on the property of the Lie bracket. It just depends on the basic property of any product. So these two spaces, the whole space and the null vector space, these have to be ideal. So they don't really count that much. So if you are going to say something as an ideal, we would actually talk about something having a non-trivial ideal or a proper ideal. So if it does not have any non-trivial ideals, you cannot say it doesn't have any ideals because it's bound to have two of them. Then you call the set simple. Then the algebra simple. Okay? Although there's a catch there. The catch is you have to actually change this somewhat. You have to add one more thing to it in the definition. We're going to come to that soon. And this is the definition of simple. Semi-simple essentially is defined this way. Lie algebra L is called semi-simple. I hope nobody here is American enough to call this semi-simple. Then you, if it has no proper abelian ideal. So even if it has an ideal, as long as that ideal, even if it has a non-trivial ideal, as long as that non-trivial ideal is not abelian, you are still okay. You are semi-simple, if not simple. Okay? Yeah.
Yes, sir.
Now, I've already said both of these definitions actually need something more added to them. I'm going to come to that. So this is not the complete definition of either simpleness or semi-simpleness. But let me ask you one thing. If L is solvable, then can it be simple? Or vice versa? Then is it simple or is it not simple, or is it that you cannot say anything? Either it could be either.
Not simple.
Why?
Because if it has sub-algebras, then which are
It might,
non-trivial.
of course, it can have sub-algebras. Algebra having a sub-algebra is not an impediment to it being simple.
Oh no.
The impediment is something else. If it has an ideal, non-trivial ideal, that's it. Okay. If it is solvable, one thing you can definitely. Okay, by the way, what is the relationship between L1 and L? I'm not talking about the definition, but what is L1 is not just a subalgebra of L, it's a special kind of subalgebra, something we have established. L1 is an ideal of L, right? Now, if L is solvable, then can L1 be the same as L?
No, if L is solvable, then there exists some n such that ln is 0, so that makes it a trivial ideal. So it cannot be simple, I think.
No, but L1 is that's
Let's just look at L1 for the time being. Ln is 0. What can you say about L1? Can L1?
L is a non-trivial ideal. Yeah.
L1 is an ideal, but it's definitely not L, right?
Yes.
Unless you're talking about the very trivial case where you started with the null algebra itself. Let's leave that out. You started with the null algebra itself. Null algebra itself is, of course, solvable, right? It's already 0. Let's leave that case out. If L1 is the same as L, which is a possibility, of course, we have seen that it happens for SO3. If L1 is the same as L, then it's impossible for Ln to be 0 somewhere down the line, right? If L1 is the same as L, then L2, L3, L4, all of them will be L. Then Ln can be 0 only if you started with the trivial case where L is itself the null vector. Let's not be that tricky. So if L is solvable, the first thing you know is L1 is not L. It's an ideal, but it's not the whole algebra or not the whole vector space. So what can you say about L in in terms of simplicity or non-simplicity? Yes? Okay, before we go to the simpler connection, simple implies semi-simple, right? That's obvious. When the algebra is simple, it has no non-trivial ideal. So the question of it having a non-trivial abelian ideal doesn't even arise. Right? Is it okay?
Yes, so
This
it
is
is
trivial.
semi-simple.
Simple, any simple, the algebra has to be semi-simple because if it has no non-trivial ideal, it definitely cannot have. What prevents a Lie algebra from being semi-simple? If it has an abelian non-trivial ideal, right? It is semi-simple if it has no non-trivial abelian ideal. That is, it is not semi-simple if it has a non-trivial abelian ideal. But it is simple, it has no ideals whatsoever, no non-trivial ideals whatsoever. So it cannot have an abelian trivial ideal, non-trivial ideal, right? So simple, all simple algebra is obviously semi-simple. But of course, not necessarily the other way around. Not conversely. That's obvious because if a particular Lie algebra has a non-trivial ideal, but that non-trivial ideal is non-abelian, then it will be semi-simple, but it will not be simple. Now let's come back to solvability. If L is solvable, then L1 is an ideal, not equal to L. So what does it tell you about the possibility of it being simple, of L being simple? You can see the definition of simple out right here on the top.
It cannot be simple then.
Okay, aren't you, if this were the definition, just this, then think about it a bit. L1, L being solvable means L1 is an ideal and it's not L. But what are the two possible trivial ideals a vector space can have or a Lie algebra can have?
If L1 is trivial, then
If
L
L1,
is not.
so when is L1 trivial?
L1
When
is
L is abelian.
Sorry.
L1 is trivial. L1 is 0 when
L1 is
L is
trivial,
abelian.
L1 is 0 when L is, so I could hear you.
Abelian.
L is
Abelian.
abelian, right? So
Yes.
for abelian groups, suppose you are non-trivial, that is non-zero abelian group. Its L1 is 0, right? It's an ideal, but that ideal is actually the trivial ideal. Okay? Yeah? Okay.
Yes, sir.
So this conclusion that if L is solvable, it will not be simple, that meets a barrier here. Because we already know that, we definitely know that if L is solvable, then L1 cannot be the trivial subalgebra that is L itself. It could very well be the other trivial subalgebra, which will be the case for abelian groups. So basically, what you do to avoid this is add a subclause to the definition of simple. Which is you just add this as a subclause to both this and semi-semis. Yeah? Then what you are saying will work. And this is how it works out. Then this actually tells you that if it's solvable, then it implies that L is not simple. And of course, This simply means that if L is simple, right? So as I said, when I define simplicity for you, you have to actually add to this additional piece, L, in the definition itself. That a Lie algebra L is called simple if it is a non-abelian algebra. Abelian algebras can't be simple. They have to be not. It has to be a non-abelian algebra which has no proper idea. This second clause, this L is not abelian, is basically being added so that statements like a solvable set Lie algebra can never be simple can be sort of properly stated without any exceptions. Okay? Any questions about this so far? None? Okay. So let's do one thing. The next day we are going to actually talk about the way that any Lie algebra. Okay, I'm not going to give a proof of that. The proof is not at all trivial. In fact, frankly, I'm not even sure whether I recall the full proof myself now. I don't think I did. But anyway, I'll not give a proof of the result because we don't really need the proof for physics. But the result is that every Lie algebra is a direct sum of a solvable piece and a semi-simple piece. And every semi-simple Lie algebra is basically a direct sum of a bunch of simple Lie algebras. Now, why is this simple? Okay, what exactly is the direct sum of Lie algebra? We are going to define the next day and then go on with this. One important thing, which is actually, okay, I made a long statement a while ago, but doesn't matter. We are going to make a precise statement the next day. But what is important is the following. What we really need to talk about in physics are not the solvable piece, but a semi-simple Lie algebra. And every semi-simple Lie algebra is essentially built out of a bunch of simple Lie algebras. And the great thing is, although we do not know all possible solvable Lie algebras till now, nobody has completely classified them. All simple Lie algebras have been fully classified. We know what are the possibilities. All possible Lie algebras, not all possible ones, but all possible simple Lie algebras are known completely. Which essentially means that if semi-simple Lie algebras are the only things you are worried about, you already know all possible options. That doesn't mean that the number of possible options is infinite. It's finite. It's actually infinite. Because it breaks up into some classes, each of which are finite. So that will essentially tell us that if you know those basic classes, you know all about semi-simple Lie algebras. You don't have to worry about anything else. That's a great result. And it so happens that among those classes, as far as we know, only a few of them, not even all of them, are actually important for physics. Okay? So this is a really important result. We are going to introduce that the next day in a big way.
Sir, I had a doubt. Sir, if L is not abelian, is it possible that L1 is abelian?
Why not? Okay, let me just remind you of the example that you saw. Okay, do you remember anything about the examples we talked about the last class? We talked about one example, which was SO3. What was the other example? Apart from SO3 and abelian, what was the other example we talked about? The Heisenberg algebra had A dagger, and the identity, right?
Yes, sir.
So this was span of these three, all possible linear combinations of these three. This was our Heisenberg algebra. if this is your L, what's your L1? You take all possible linear combinations of A, dagger, and I, which of course is an arbitrary element of this Heisenberg algebra. Take its commutator with something else. What are you going to get?
Okay.
The span of I, right?
Yes.
Multiples of the identity. Is this abelian? Of course it is. Right?
Yes. Okay.
So L2 has to be 0. Which means that this is an example of the solvable Lie algebra. By the way, you should have realized, if you thought about a bit, that if any solvable Lie algebra exists, say if ln is 0,
Yes. Yes. Yes, sir.
then ln minus 1 gives you ln equals 0, then you have ln minus 2, which did not give you 0, but ln minus 1 gives you 0. So ln minus 1 must have been abelian, but ln minus 2 wasn't. Right? So you
Oh,
must have
so actually, my question was like, if it is giving 0 at the end, so the previous one
it's
has to
giving
be
0 at
abelian.
the end, but the previous one was not giving you 0, right?
Yeah, yeah,
The
but
one which is
then
giving
the
you 0
previous
has
one
to be
has to
abelian.
be abelian. Okay.
The one which gives you 0 has to be abelian, but the previous one wouldn't have been abelian. If the previous one were abelian, you would have stopped at that stage.
Yes. Okay.
The very notion of solvability, that is the very fact that you have non-abelian solvable groups. And this is an example. There's a non-abelian solvable group, right? Stops at the second level. Since L2 is 0,
Yes.
L1 has to be abelian. But because L1 is not 0, L or L0 has to be non-abelian. Yeah?
Yes, sir.
Okay, we are going to talk about the general result about classification of the algebra. That's as far as we can. As far as we can, because all possible solvable Lie algebras have not been classified fully. Okay? But all possible simple Lie algebras and more importantly, all possible semi-simple Lie algebras have been classified fully because all possible simple Lie algebras have been classified. So we're going to talk about that the next day. But before I go there, let me talk about one thing which will be very useful in the long run. It's always useful anyway in the first place because remember, when we talk about groups, for example, groups are abstract. But when you want to apply them in a physical situation, or when we also want to get a more concrete handle on them, what we usually deal with are not the groups necessarily, but with the representations, right? Representations are basically, okay, a representation of a group. What was that? It was an isomorphism from the group to a special kind of group. What was the second special kind of group? If two groups are isomorphic to each other, then if they're not even isomorphic, homomorphism would also be. Two groups are homomorphic if they have the same structure. But when we talked about representation, we talked about the homomorphism between the group that I'm talking about on the one hand, and a special kind of group on the other. The special kind of group was what? Yes? I'm, of course, going to talk about representation of algebras now, but let me just remind you that we already have spent quite a lot of time in the first half of the semester, and this is way too early for you to have forgotten about that. What is it? It's a homomorphism. Representation of group G is a homomorphism from
Set of linear operators. Invertible linear operators.
right. Homomorphism from G from G to GLB. We have G some vector space, right? Is that okay?
Right.
And just like you have linear representations, you have, along with that, you also have matrix representations, which is basically what you get from a linear representation once you choose a basis. So this was for group. Similarly, so what's the special about GLB? It's basically effectively a bunch of matrices which can be multiplied together, which can all be inverted and so on, and which mimics the properties of the group as closely as they can. I say as closely as they can because all you need is a homomorphism. So you can have something as trivial as every group element maps to the identity matrix. Or if you have the irreducible representations, every group element maps just to the number 1. That's a possibility. Okay, so it does not really have to mimic the group in its entirety. You may have the group may be not abelian, but this particular from G to a subset. If you insist on homomorphism to be onto, then you should sit to a subset or subgroup of GL. Right? If in the definition of homomorphism, all you care about phi G1 G2 is phi G1 equal to into phi G2, then you didn't have to specify this. But usually, especially for convenience, we often also add it's an onto map. A homomorphism from G1 to G2 is a map from G1 onto G2, which has phi G1 G2 equals phi G1 phi G2. If you want that, then here it's not necessary that G maps to all of GLB. It may map to a subgroup of GLB. And it could also be written down in a bunch of matrices. So, what can you, by analogy with this, what would a representation of a Lie algebra be? Now, what is a Lie algebra at its heart? It's a vector series, right? Which has a bracket operation. But the elements are vectors. So representation of Lie algebra will L is a homomorphism between L and some vector space V. So when you talk about specific concrete vector space, that becomes a sort of representation or realization of the Lie algebra. Of course, what is important is the homomorphism fact, that basically what you want, when you say homomorphism, what you want is this map phi, which maps you from whatever Lie algebra L you have, which is itself a vector space, to elements of the vector space V. You must have this property. If you take the Lie bracket of 2 elements of L and then map it to your vector space, you should basically have the Lie bracket and now here I have to be very specific. This of course cannot make sense if V is an arbitrary vector space, right? Is that okay? Why can't this make sense if V is an arbitrary vector space?
Because there won't be any Lie bracket defined on it.
Yeah, an arbitrary vector space will not have a Lie bracket defined on it, and here you do have a Lie bracket defined on it. Now I can make this more abstract, but here what I really should say is it's not really V, but basically some space of matrices, let's say. Remember, a space of matrix n by n square matrices. This is a space of n by n square matrices, which is a vector space in its own right. You can add two n by n square matrices to get an n by n square matrix. and multiply an n by n square matrix by a number to get another n by n square matrix. And under these two obvious operations, it becomes a vector space. But this also is a Lie algebra because you can take the square bracket, Lie bracket, you can define the Lie bracket on matrix R by simply saying, what is the Lie bracket of two matrices A and B?
AB minus BA.
AB minus BA, just the commutator. Okay. Note that the bracket x comma y within arbitrary elements of L could be rather abstract operation. But what we are really doing is mapping that to a more concrete operation. That is, you have square matrices, you are doing AB minus B. Okay? Right? Actually, the map is really, at the abstract level, the map is not to matenard. Matenard is basically the matrix representation of that result. The map is really here over automorphisms of a vector space. Do you understand what that is? These are really maps from V to V, right? So if you have maps which map from V to V, you can of course form their product. And that product actually is an associative product. That's very, what is the product of two automorphisms? Two automorphisms are two maps which carry V to V. Their product is obviously what? When you have maps between spaces, what is the product?
It's between the same spaces.
No,
So
what does the product mean? When you say you have a map F from V to V, another map G from V to V, what is FG?
It's also an automorphism.
But what is it? It is an automorphism comes later. Let's first define what FG is. How do you define
FV times GV.
No. That makes absolutely no sense. FV may not be FV is
F
what?
of G of V.
F of G of V. Always. It's always a composition. Remember, FG was defined to be FG of V is F of V into G of V, or F of FG on some matrix, some manifold element M was defined to be F of M into G of M, where these maps were maps onto a space where product was defined, namely real numbers. You are confusing maps from the manifold to real numbers. In this case, these are maps from V to V. They can't be multiplied. Their results can be multiplied. Two vectors, how do you multiply them? When you have automorphisms, then product, well, you should say product with air quotes around them, or actual quotes around them, if you're writing them down. The product of two matrices, or sorry, product of two transformations is simply by composition. You do one after the other. The one very important property of such a product is that this product is always associated, right? Is that okay?
Yes, sir.
So if you have aught V, that is set of all automorphisms of a vector space V, then what you automatically end up with is an associative algebra with a naturally defined product on aught V. And because you have that, you can always define a Lie algebra by just using AB minus BA. Remember, every associative algebra gives rise to a Lie algebra. And therefore, AB minus BA is the obvious thing to do. So this is what a representation is. You have some abstract Lie algebra L, which has some bracket operation. You map L to the space, set of automorphisms of some vector space. Some concrete vector space, take its automorphisms, map L to that, but map it in such a way that the map of the Lie bracket is the commutator. So on the left, the Lie bracket can be anything, but on the right, the Lie bracket is actually the commutator in the sense that you are doing phi x, phi y, or minus phi y, phi x. Remember, phi x is an automorphism, so is phi y. Phi x, phi y is just do phi x after you do phi y. So phi x, phi y minus phi y, phi x is a valid Lie bracket on that state, on that set, odd way. And if you have a homomorphism like this, you call this a representation. Okay? Now, why are representations so important? Just like with groups, representations give you a much more concrete way of handling abstract Lie algebra elements. That's the first and foremost need. Now, can you think of some very obvious Lie algebra homomorphism, or some representation which is very obvious? So obvious that we are going to call it a trivial representation. Remember, the trivial representation of group is every group element gets mapped to the number 1. Or if you're not looking for irreducible versions, every group element gets mapped to the identity matrix or the identity operation if you're talking about linear operations. So what is the most trivial thing that you can do in the case of Lie algebra? Yes? The map which takes L to some space, which of course has to be specified, but X maps to, say, some obvious space like R. R is actually is in one correspondence with odd V for a particular V. Let's think about which one that is. But which number can you map X into? Well, R here simply means multiply by the number R. But what is the obvious number that X can map to? So that this condition will always work.
The number X.
X is a bracket. There's no such thing as number X. X is an element of some Lie algebra. X is not a number. And there is no such number associated with X. But remember, when you talked about the group element, you didn't care what the group elements were. The trivial representation was take every group element, map them to the identity matrix, or map them to the number 1. Here, take every group element, map them to what? Every algebra element, and you want to ensure that this will work. That is, after you do the map, whether you do this after or before the map, you get the same result. Let's not worry about R right now. That might be confusing you. Let's talk about L as some homomorphism between L and not odd V, but actually some algebra of odd V. For the same reason, it may not be all of odd V. So what kind of automorphism is it which ensures that this will happen trivially no matter what X and Y is? As is simple. There's a null map which maps every element of the vector space to 0. Is that an automorphism? Yes? Okay, I think I've messed up. I messed up simply because I forgot what an automorphism means. I messed up because, okay, I've forgotten these fancy names. So next day I will definitely check up the names and see this again. Is the automorphism meant to be invertible, by the way? Just remind me, I've forgotten that. Or is it just meant to be a map from V to V? I think when you say automorphism, you also, okay, this is where my memory is playing tricks on me. I don't remember what an automorphism means. Can anybody help me out? Is it meant to be just a map from V to V? The linear map from V to V. or is it meant to be an invertible linear map from E to D? Yes?
Invertible.
If it's invertible, then I didn't mean that. Okay, I meant linear actually. But any linear map from E to D will do. It doesn't have to be invertible here. I think you're right. I now seem to recollect that automorphism, of course, means invertible maps. So we are not talking about that. We are talking about linear map from E to D. Maps which preserves a linear structure but doesn't necessarily have to be invertible. So the most obvious such map is a null map, which takes any element, maps it onto 0. But it's obvious that if you compose two null maps, in whichever order they give you the null map, the commutator is also the null map, right?
Right.
And that means that this will always work. Remember, on the left-hand side, you're taking the bracket. The bracket could be non-trivial, does not necessarily have to be 0 or anything. After the original, the algebra may be non-ambiguous. But when you apply phi on this, you get the null. On the right-hand side, what happens? You get the commutator of two null maps, which is, of course, a null map. Okay? So this is, and in case you want the smallest dimensional thing, that is, you want V to be as small as possible, one dimensional, then, of course, this map is simply multiplication by a number, and the null map is multiplication by 0. So every element of the Lie algebra is mapped to 0. 0, not 1. Remember, that's the basic difference. In a group, every element being mapped to 1 is a group homomorphism. For Lie algebra, if you want to maintain the structure here, after all, if you insisted that, okay, every element of a Lie algebra maps to 1, can that obey this condition? Phi x will be number 1, that is multiply pi by 1. Phi y would be multiplied by 1. These two, of course, would end up having a 0 commutator, right? But on the right hand side, you would get 1. So these won't match. So what works for a group where you have a product does not work for a Lie algebra. That's what I wanted to emphasize. The trivial representation of Lie algebra is map every group algebra element to 0, or to the null map of whichever space you're talking about. Is that okay?
Yes, sir.
Now, in the case of group, we found one representation. Remember, for a representation, you need to have a vector space, right? A representation has to map G onto GLV, the operators acting on some vector space, right? So it needs some specific vector space. Now, if you just have a group, you could manufacture a vector space for the group, right? Which is
Algebra. Group
the
algebra.
group algebra, right? And therefore, you always could land up with one representation no matter what the group was, which is, apart from the trivial ones, etc., which is a regular representation. The one will make the group act on itself. Well, by a very same kind of logic, a regular representation of a Lie algebra L is basically a homomorphism, a special kind of homomorphism, of course, from L to instead of all linear maps. Acting on L. So what is this representation given by? It has another name, and let me just point out what that is rather trivial in a sense. So it has to take an element x, so let's call it small x, of course, that's what we have been calling these things. belongs to L, and X gets mapped to some linear operation on the Lie algebra itself. Now, this linear operation we are going to call add X. Okay? X maps to add X, Y maps to add Y. So, this is really add acting on X, but the standard notation is add suffix X. It's just notation. Okay? Now, add X, of course, is a specific linear operation acting on the Lie algebra. It's a very easy thing. Add X acting on Y. After all, if you want to specify what a linear operation acting on a vector space is, what you should do is tell me what it does to every vector, right? So I'm telling you. Let me remind you that X and Y, these being Lie algebra elements, are also vectors. Lie algebra being a vector space. So add X is a linear operation, acts on Y to produce this. So this is where the Lie algebra, Lie bracket structure of a Lie algebra and the vector space structure of a Lie algebra gets married together. You define add X via this condition. Okay? Clear? To every element X of the Lie algebra, you assign a linear operation on L called add X, whose action on any vector of L is simply take the Lie bracket with it. Okay? Make sense?
Yes.
Now, of course, you have to check whether this is at all a linear map, number one, which is trivial, right? Add X acting on Y1 plus Y2. By definition, is X bracket with Y1 plus Y2 and Y1 plus Y2. X being a bracket, X being a product. Sorry, the bracket being a product. Here is X comma Y1 plus X comma Y2. So add X acting on Y1 plus add X acting on Y2 and so on. Also, add X acting on CY will be C times add XY. These are trivial things to prove. That this is linear is trivial too. But remember, we are not looking at any linear map acting on the Lie algebra. We are looking for a representation, which means it's something which should respect the operation of the Lie bracket itself. That is, what was the Lie bracket for L must come out as a commutator in the representation. So let's look at this. Add X is a linear operation. Being a linear operation, of course, you can multiply them together, right? Multiply meaning do one after the other. And you can, of course, multiply them in the other order and therefore can also figure out what the commutator is. So let's try to figure out what this is. Add suffix X, add suffix Y commutator. And of course, the commutator is another linear operator, and the best way to figure out what a linear operator does is to make it act on some vector element. So Z, X, Y, Z, all of these are elements of L. Add X is a linear operation on capital L, add Y is a linear operation on capital L. I'm trying to figure out what the bracket is. What is the bracket? This is by definition add X on add Y Z, right? Minus add Y on add X Z. That's nothing but the definition of the commutator bracket, right? And now you get, if you write it down, what is this? X's bracket with Y Z's bracket, right? That's what this is. And the other one is just the same thing with Y and X interchanged. Yeah. Okay, okay. Does this make sense?
Yes, sir.
But now, let's take a note of this. Let's leave this one as it is. Let's just change the second one to this. I can, right? I've flipped over xz2 minus to get a minus zx, and because this bracket is linear, the minus will come out and become a plus. But now, what is this quantity?
Negative of Z XY.
Right. It's negative of zxy. That's the Jacobi identity. And is the same as the bracket of xy,
Z.
z. Right? Or this is actually add,
YX.
no,
X,
add
Y.
xy. Not yx, by the way. Here I've changed the sign once by just flipping these two. So minus plus plus. But this works for all z, right? No matter which Lie algebra element you pick, the commutator between add x and add y is actually add of the commutator, add of the bracket. Commutator of add x and add y is the add of the bracket of x and y. So even if the original bracket xy was not a commutator, but was any Lie bracket, is being represented by this commutator operation. In other words, you always have this. This is a genuine commutator bracket of the mapped, the value that xy the bracket maps to. So this is a representation. A very important representation called the regular representation of a Lie algebra. Every Lie algebra, by virtue of being a vector space, has this representation. Okay? And we will see later that this actually, thinking in terms of adjoint x's, actually make many of the even familiar results which I've used before actually turn out to be very easy to understand. For example, let me just give you a quick familiar example. In the SO3 or SU2, let's call it SU2, doesn't matter, same thing as far as the algebra is concerned. You have Jx, Jy. I'm putting h equals to 1 equal to I Jz, right? The I is simply this phase is addition factor of I thrown in because you wanted Hermitian operators. But you also, you don't, when you can work out the Aguda algebra, you essentially use these combinations, J plus minus, which are Jx plus minus Ij, right? Familiar things? Yes?
Yes.
But basically what you are saying is something like this. Let's focus on add Jz. This is a linear operation on the acting on the space of Jx, space packed by Jx, Jy, Z, right? Now, add Jz, acting on Jz, how much is that? This linear operator acting on Jz is what?
Commutator of JZ and JZ.
What is that?
0.
0.
But you can think of, okay, there's a reason why I'm writing it like this. It's 0, but it's 0 into Jz. Add Jz acting on J plus minus. What is that? These are, of course, the ladder operators, but what is this add Jz acting on J plus minus?
Plus minus J plus J minus.
Plus minus J plus minus, right? Now, when I write it this way, does this strike you as something Jz, J plus J minus? Jz is a bit trivial, but J plus and J minus. What are they in relation to add Jz? Add Jz is a linear transformation on this space spanned by Jx, Jy, Jz, right? J plus minus are elements of that, although complex combination, but still elements of that. But what is J plus minus in relation to add Jz as seen by this expression? Forget that add Jz tells you take a commutator. Forget that. Add Jz is a linear operation. It acts on J plus minus, J plus, let's say. Gives you J plus. This linear operation.
So Is it a
I,
parity operator?
Oh,
no,
you're actually
eigenvector.
focused on. If it is a priority, you're focused too much on the plus or minus. That's not really the important thing. But I heard something.
Eigenvectors.
These are eigenvectors, right? Jz, J plus, and J minus are nothing but eigenvectors of at Jz. All you have done here is diagonalize this operation at Jz and found the corresponding eigenvectors. In fact, if you actually ever wondered where did we come up with J plus minus from, we had this Jx, Jy, Jz, right? How did we arrive at this J plus minus thing? The answer is we just looked at the eigenvectors of at Jz. Okay. And by virtue of the properties of the fact that at Jz actually meant commutator, you could see that J plus was a raising operator for eigenvalues of Jz. J minus was a loading operator, and Jz itself was something which kept the eigenvalue unchanged. That's the theory. Right? Jz acting on a Jm eigenstate gives you the same eigenstate, right? It doesn't change the M value. J plus raises by 1, J minus lowers by 1. Those are nothing but these eigenvalues of at Jz. Okay? Right? So this is very familiar. I'm just putting this in a slightly different language. But why is this very useful? Because you already know why this is very useful. This allows you to reconstruct all sorts of full representations of the SU2 algebra. You didn't call it that perhaps. You just call them angular moment by eigenstates. But you could create vector spaces where, which were invariant under the action of Jx, Jy, Jz. And you could completely figure out what Jx, Jy, Jz does to every state there. Using just these properties. You could figure out invariant eigenspaces, spaces of Jx, Jy, Jz. Invariant spaces on which Jx, Jy, Jz acted. Not eigenspaces, but and the key to that was take that Jz operator and find eigenvectors of that. The eigenvalues, the plus minus 1 and 0, came in as a result of the calculation. Now, having said this, let me just give you a glimpse at the future. Suppose you wanted to do the same kind of thing, find out all possible states and actions of all operators, right? That's what this does. You know how what Jx, Jy, Jz does to any of the Jm states, don't you? You know what J plus, J minus, and Jz does, and therefore you know what Jx, Jy, Jz does, right?
Right.
Okay, but suppose you had a bigger Lie algebra. What's the other next biggest Lie algebra that you have heard about? I don't have SU2 here. What's the next one? What comes after 2? Well, what comes after 2 is 3, right? You have all heard of the Lie algebra SU3? Yes or no? Have you heard of it? Have you heard why it's important? At least in particle physics context, either as something which gives us the quark model or something which in this group focal version gives us the modern SU3 cross SU2 cross U1 version of a standard model. But okay, the point is we are going to talk about SUN in general soon. But let me just point out that in SU3, you have more generators, more than 3. That's easy to understand. The group SU2 can be completely parameterized by 3 parameters, so you have 3 generators. SU3 is actually completely parameterized by 8, so 8 generators. Now, let me just ask you one thing. Here, I took add Jz and found its eigenvalues and eigenvectors. Could I have taken add Jx and done the same? Or is there something special about add Jz? Or add Jy? Is there something very special about add Jz? Okay, adjacent bit might sound a bit not so familiar, but this is what all we are really talking about, right? Commutators with JZ. But why JZ? Why not JX or JY? Could I have done angular momentum algebra by choosing JX instead of JZ? Forget Lie algebras. We were doing angular momentum before, right? And there we chose JZ as something special. Did we have to?
Sir, we could have chosen
Anyone.
like,
But
yeah.
could we have chosen two of them together?
No,
Why not?
they cannot be simultaneously diagonalized.
Why not?
They can't commute.
Because not because JZ and JX does not commute, although that's at the heart of it. Because at JZ and at JX, for example, does not, right? How do I know that at JZ and at JX do not commute? Because the commutator is nothing but add of JZ JX, which is essentially at JY, right? Not 0. Remember, this formula tells you that the commutator is of the adjoints essentially mimic the original commutators. So at JZ and at JX do not commute, and because they don't commute, they cannot be simultaneously diagonalized. And take any one of them. Well, when you're talking of SU3, there are 8 generators, and 2 of them mutually commute. Okay. Out of 8, 2 actually commute with each other. What does that tell you? How we know about that? All that we are going to come later when we talk of specifically of SU3 income more generated. But if two of these generators commute among each other, then their corresponding adds can actually be diagonalized together, right? Is it okay? Adds are just linear operations acting on a finite dimensional vector space. So just think of them as some matrix acting on some vectors, some column vector. If two such adds commute, if two such generators commute, their corresponding adds commute, and because the adds commute, the adds can be diagonalized together. What that means is instead of having an raising or lowering operator, which just raises and lowers one number, in SU3 you will have an operator which raises or lowers 2 numbers at the same time. 2 numbers meaning eigenvalues of those 2 operators. So basically SU3 will be very much like SU2. It's really not going to be that much more difficult, except that every state will be characterized not by one eigenvalue. Here, remember, in SU2, every state is essentially characterized by M within a particular ADEP, that is within a particular J value sets. M is what characterizes a state, only one number. In SU3, you will need 2 such numbers. Within each ADEP, you will need 2 such numbers. Each of which will be changed by corresponding raising lowering operators, which are essentially the numbers are nothing but eigenvalues of those 2 operators which commute with each other. So which can be simultaneously diagonalized. And the corresponding shift operators, just like you have raising lowering operators, you will have shift operators there. But the shift operators change both of these eigenvalues, not just one number. And therefore, when you draw the thing out, instead of having points on a line where M is 0, then shifts to J plus shifts that to 1, J minus shifts that to -1, J plus again shifts that to 2, and so on. Minus 2 and so on. If you had something where 2 such pairs of numbers were being shifted, and you wanted to draw that geometrically, how would you draw that? You have one number, you draw that on a lumbar line. Class, well, I don't even know, it's perhaps kindergarten stuff or class 1 stuff. Drawing integers on a number line. So 2 such numbers, what would you have to do?
A grid. 2D grid.
Well, grid may not be that great, but at least it should be 2-dimensional. Grid is some kind of grid, but the numbers may not be related to each other very nicely, and so on. But it will be some 2-dimensional figure. Okay. And as the shift operators act, One point on the two dimensions is shift to the next point and so on. And I'm pretty sure all of you have seen such diagrams. Have you seen diagrams like this?
Yes.
The eightfold way quack model and so on. Those diagrams are nothing but
Yes.
these diagrams, nothing but these things. Okay, that is, I'm just giving you a sort of appetizer for now. We are going to show how to get these diagrams and way more than that. Not only just for SU3, but for arbitrary cases, or at least for all semi-simple D groups in principle. Though there may be, of course, if a semi-simple D group has 4 commuting operators or 4 D brackets which vanish among basis vectors, then the same picture would have to be really drawn in 4 dimensions, which we can't draw on a piece of paper. The basic idea stays the same. SU2 and SU3 are pretty straightforward to draw because SU2 is basically one-dimensional. At least the shifting is one-dimensional. You can just draw a line. You don't even bother to draw a line because a line is so simple, you don't even bother to draw it. SU3, to understand that properly, you draw a two-dimensional plane with basically these. You have operators which take you from one set of M1, M2 to another set of M1, M2, and so on. Why do they move in this particular manner? Why do you get a kind of hexagon-like thing, etc.? That will be clear once we talk about the exact diagonalization of these things, which will come soon. Not next class, but pretty soon. Okay, I think I've already given enough for today. If you have no questions, I can wrap up. Do you have any questions? That is, if not, then let's wrap up for the day.